I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team. It's our job to help you get the best out of the Oracle database. There's a recognition that the Oracle database is a fantastic piece of software, but we as a company haven't done too great a job at helping people actually use it. So part of my job, or entire my job, is to help you be more effective when working with Oracle. And so I'm creating various resources to do that. I've got my blog, my YouTube channel, The Magic of SQL. If you want to reach out to me about anything I discussed today or any other questions you have about Oracle, you can get in touch via Twitter or my email, which are up there. Or you can reach me through my official channel if you have problems. I'm now part of the answer team for Ask Tom. Many of you may be aware of this if you've been working with Oracle for a while. Last September, Tom Kite decided he was going to take a sabbatical. So myself and Connor, the other SQL advocate, stepped in, and we're now answering questions on Ask Tom. So if you've got problems, things you're struggling with, don't understand about Oracle, feel free to ask them here. But I also want to know not just how you're struggling to develop, what could we do better in terms of making the product better for you? How can we help you be more effective when working with the Oracle database? So if you've got specific technology questions, ask them here. If you've got more general, how could we be better, how could we improve questions, then just reach out to me directly. Now, I am a member of Oracle now, so you can't trust a word I say. I'm not talking about futures here, so none of this should be really relevant. So let's get started properly. Any of you who've spent more than a couple of minutes trying to tune SQL queries have almost certainly encountered this. They're going, well, Oracle should be using my index. I've got a query, and Oracle's chosen to do a full table scan rather than use an index. Why has it done that? As far as you can tell, you've done everything right. You've got all the columns in the where clause. There's not any functions on them or anything else like that. Why has Oracle decided to go for a full table scan rather than use an index? Well, the simple answer is it's down to the cost. Oracle's decided that the cost of using the full table scan is less than the cost of using the index. But that's a bit of a non-answer, really. So what I'm going to do today is explore some of the reasons why that form the basis of the cost, why Oracle will choose to use an index versus a full table scan. But first, I'm going to talk a little bit about chocolate. So I've got two young daughters, and they unsurprisingly love chocolate. However, like all good three-year-olds, they're very picky. They don't want any of the sweets. You know, they love M&Ms, but they don't want any color. They want specific ones. They want the red ones. So what they do is they come to me and say, Daddy, please, can I have some red M&Ms? Now, I have to be sure I have to give them the red ones, otherwise I'm going to face a temper tantrum, and I don't want to deal with that. So what I can do is, I've got a huge stack of M&Ms here. I can pick up a few bags at once, and I can open them up and sort their contents out. So I can empty them out, look at the color of each sweet, see whether it's red or not, and if it is, put it to one side so they can have it, and then put them back in the bag. And I can keep doing that, picking up bags at a time, pulling out the red sweets, till I've got all the sweets that I'm interested in. However, I've got a bit bored of doing this every time they want sweets. So what I decided instead is that as soon as I buy some more bags of M&Ms, what I'll do is write down the color and location of every single sweet. So I go through, come home from the shops, get the bags, open them up, say which colors are, write them down in a document, and then put them back in the bags. So when my daughter comes to me now and says, Daddy, please, can I have some red M&Ms? Instead of having to pick up the bags, open them up, and filter their contents, what I can do is I can just go to my handy document here. I can go to the red section, start up there, find the location of the first red sweet. So pick it up, bag 100, open it up, get that sweet out, and then go to the next one. So the next one is in bag 70. So I go to bag 70, pick it up, open it up, get the next one out. And so on and so forth. Keep walking down my document, back alternating between the entries here and the bags until I've got all the red sweets, or enough to make the girls happy anyway. So this is kind of fun, interesting story, but what's all this got to do with Oracle? Why does this relate to indexes and full table scans? So imagine here that the M&Ms are a table in the database, and every M&M is a row in that table. So just like your table will have columns with various properties, so things like the color, what flavor it is, expiry date, its weight, and so on. So they've got a number of attributes, and all these suites have various attributes. And my document is like an index on the color of those suites, the color of the M&Ms. But the bags themselves also represent something important. Does anyone know what it is? Can anyone tell me what block? Exactly. So the bags represent a block. So just like when you buy M&Ms, you get them in a bag, you don't just kind of scoop them out in your hand and walk around the shop and pay for them. You always buy them in a bag. Rows in Oracle are always stored in a block. They're not just randomly lying around on the disk somewhere. And just like I pick the bag up, when I want an individual suite, an individual M&M, I'm not just picking up the one that I want. I pick up the bag and then have to pick out the one I'm interested in. It's the same when you fetch a row in Oracle. It picks up the block and gets the row that you're interested in. So if you only want one or two rows from the block, there's potentially a lot of overhead. You're potentially picking up a lot of stuff you don't really need. And my two approaches, so my first approach where I was picking up several bags at once, that's like a full table scan in Oracle. And the second approach where I had my document writing the location of all the suites is like an index range scan. So with the full table scan, just like I was picking up 3 or 4 bags at once, Oracle's able to do what's called a multi-block read. That means it's not just picking up one block at a time, it's picking up several blocks, filtering them to see whether they match your where clause or not, discarding the ones that aren't, and returning the ones that are up to the client or to the next step in the execution plan. And with the index range scan, I'm only ever picking up one bag at a time. So I go to the document, find the location of the next entry, pick up the bag or the block that that relates to, get it, and then I have to go back to the index to find the location of the next suite, the next row. So this is all very well and good, but which approach is faster? So I'm finding all the red suites here. There's so 1 in 6 of the suites are going to be red. There's 6 different colors. Which approach is going to be faster? Who's going to vote full table scan? A few of you. Who's going to vote index range scan? Slightly more, slightly more. Who's sitting on the fence and not deciding? Who's not going to commit? Yeah, Alex. I know. Anyway. Well, let's look at how much work they're going to do. And we measure work in terms of the number of bags or number of blocks that we access. So with the full table scan, if I want to read all the red rows, so I want to find every single red M&M, I pick up each bag once, open it up, filter the contents out, put it back, then move on and read all the rest of the bags. However, with the index range scan, with 30-ish M&Ms per bag and 6 different colors, I'm going to have to visit each one about 5 times. So that means I'm picking it up and putting down, picking up, putting down each bag 5 times. So in terms of the amount of work I'm doing here, it's about 5 times more for the index range scan compared to the full table scan. So here, it's actually the full table scan, which is the more efficient approach. I'm fetching a significant fraction of the rows from the table, so it's better to do a full table scan. Let's flip this around a little bit. Let's imagine Mars run a promotion. And they have a thing, imagine I've got 100 bags here, and they're running a promotion. 1% of them have a silver suite. So 1 bag, 2 of a lucky, 0 of one unlucky, are going to have a silver suite. Open it up, you dial some premium rate number, give them all your details, and they give you free M&Ms for a year or whatever. Which approach is going to be faster now? Which approach is going to be better? Who's going to vote full table scan now? Just one, two brave people. An index range scan now? Yep. Yeah. So if we compare the work done here, the full table scan is still having to look at every single block. It's still picking up every single bag, looking at every single row to see every single suite, whether it's silver or not. And we have to do that till we've read them all. However, with the index range scan, we've got our document, which tells us the exact location of the one, maybe two if we're lucky, suites that are silver. So all we have to do is go to the index, go to the one single bag that has the silver suite in, open it up, and we've got it. So the index here is the hands-down winner in terms of the amount of work it's done. It's substantially less. So you can see, so the key point, so index range scan's the winner here. So the point here is that the cost or the amount of work that a full table scan does is constant. It doesn't matter whether you fetch one row or all the rows. If I'm just getting the one silver suite or every single suite, I still got to pick up every single block, check whether they match their where clause, and pass the results up to the next stage of the execution. The index range scan, however, will do an amount of work proportional to how many rows I'm actually fetching. So the more rows I'm fetching, the more work it does, the slower the query becomes. And at some point, you reach the crossover point where an index is more efficient than a full table scan, and vice versa. And this is what the cost-based optimizer is doing. So when you submit a query to the database, it looks at this. It looks at your database statistics. It says how many rows are there in the table, how many blocks do they consume, how many different values are there, and so on. And it estimates, and it kind of goes, well, I think I'm going to do this much work for a full table scan based on how big I think the table is. And I think I'm going to do this much work using an index range scan based on how big I think they are. So note I say estimate, because this is based on the statistics it's gathered. So if the table's changed significantly since you last gathered stats, this may be out of date, and its estimates could be wrong. But it works on the information it has and does a best guess about which is going to be cheaper. And as a result, this is one of the key components, what I've just discussed, and one of the key components of that figure that we call the cost in Oracle. However, I've made a really big assumption when discussing all this when it comes to the efficiency of an index. Does anyone know what it is? I've jumped ahead a little bit, which might have given it away. Yes? Yeah, well, so it's that they're random. Or more importantly, they're random relative to the order they are in the index. So what if we make a different assumption, and that the order they are in the index exactly matches the order they are in the bags? So this bag here, for example, may only contain blue M&Ms. The next one might only contain brown, and so on. How does this affect the work that Oracle thinks it's going to do? Well, so we have a situation like this. So our first 5 bags only contain blue suites. Now the key thing to notice here is that if we want to find all the red ones, or all the ones of a single color, we no longer have to visit every single bag. We only actually access the ones that match our color. So if I've got my bags lined up here, these are blue, brown, green, orange, red, I only pick up my red one to get those red suites out. And even more importantly, because the next few suites are all red, I can keep this bag in my hand. So I don't have to keep picking it up and putting it down every time. I've still got to go backwards and forwards between the index and my bag, but I'm not having to pick up and drop the bag every time. I can keep it in my hands and just keep reading it. This reduces the amount of work you do using an index substantially. Like I say, we cut out half the blocks, or 5/6 of the bags. We no longer need to visit them anymore. We can just restrict to those ones, and we're only switching bags when we've exhausted all the different suites. So now, the amount of work we're doing is proportional to the number of different bags that actually contain red suites. So if we've got 100 again, and roughly 1 in 6 of them have red suites, so I'm only accessing about 16 bags now. And the work it does becomes a lot closer to the work it does compared to the full table scan. And this is what Oracle calls the clustering factor. So this is a measure of how well the data in the index matches the data in the table. So the indexes are ordered data structures. When you add a new entry into it, it has to go in a particular location. So if it's on color, it sorts it alphabetically according to the color, and then it also appends a row ID. So I kind of misled you slightly at the start. The row ID points to a particular block, so all the red entries will kind of be lined up this. So you won't go 2, 3, 4, 3, 4, 2, 3, 4 in the index. It will go red 2, 2, 2, red 3, 3, 3, red 4, 4, 4, and so on. So I misled slightly at the start just to make a point. But this is, Oracle measures how well this order in the index, this logical order that it's enforced, measures the actual order it is in the table. Like I said, this comes through in the clustering factor. Lower numbers are better. So, and it varies from the number of blocks in the table, so that's the kind of like baseline lowest, up to the number of rows in the table. The lower the clustering factor is, the more efficient or the more effective an index will be to actually execute your queries. So at this point, I'm just going to jump into a quick demo to show you how this works. So I've got my table of M&Ms here, and we can see we've got and I've got indexes on the ID, the insert date, the color, and the weight. And looking at these dictionary tables, we can see the clustering factor here for them. So the number of rows, we've got 5,500 rows in this M&Ms table, 41 blocks, and we can see that the insert date and the primary key, M&M ID, are perfectly clustered. So the order they are in the index exactly matches the order they are in the table. Color, kind of, sort of, okay. You know, it's what you notice is about 6 times the number of blocks, so 40 blocks times 6 is slightly more than the clustering factor. And that's because, like I say, M&Ms for a given color will all be next to each other in the index and so on. So you have all the red ones lined up nicely in order, then you go on to the yellow ones nicely in order. Well, start with the blue ones, and so on. So from this, you would expect the index on the primary key to be much more effective than the index on the weight, which has a really high clustering factor, 4,500. That's almost as many rows as there are on the table, pretty much as bad as we can get. So just to kind of prove this, I've got this query here which fetches number of rows from the table, and I will just get the execution plan for this. So everyone, how familiar are people with execution plans? Yes? No? Sort of, maybe? Sort of, yeah. Okay, so a little bit of each. So we can see here what Oracle's done, and it's chosen to go for a full table scan, and it's accessed 548 rows here. So that's how many rows this query fetches. And in the amount of work it does, this CR buffer gets, so how many block reads basically, is 44. So let's just pin that for a second. I've lost my cursor. So let's just pin that, and then compare it to the primary key. So between 1 and 550. So this is actually going to fetch pretty much the same number of rows, actually slightly more when it comes back. It's thinking very hard. Okay. And we can see here it's gone for an index range scan. And but it's actually fetched 2 more rows than the index on the weight. But it's done noticeably less work, only 19 gets versus 44 for the full table scan. And that is because the data is much better clustered by the primary key than it is by the weight. The order the data is listed in the index much more closely represents the order it is in the table for that primary key value than it does for the weight. So it's much more effective. So you can see we hit fetching basically the same number of rows. Really, this clustering factor has a big impact on how effective they are. So let's, if I get my cursor back, see, let's take this a bit further. If we force Oracle to use an index for that same query on weight, so we'll get the same number of rows on here, we'll do that. So we'll now use an index, but we'll see it does a lot more work. And it will come back. So it's fetching the same number of rows, 548, but look at this, look how much work it's doing, 463 buffer gets. That's telling us there's only 40 blocks in the table. It must be picking up and revisiting the same block multiple times. It must be doing it more than once for that number to be so high. And that's because the order of the weights are completely random to the order in the table. You know, it started those at 0.7 of a gram, which happened to be near the start, and the next one further on, and so on. So just to kind of show how, and so when does the index become effective for weight? Well, I've forced the index here because it still doesn't always quite choose it, but we're fetching a much smaller fraction, so just 39 rows, less than 1% of the table, notably less than 1%, and it's only just more effective than a full table scan. It only just does less work than a full table scan to fetch less than 1% of the rows. But what about this primary key, this perfectly clustered primary key where the order of the data in the table matches the index exactly? Let's take a look at that. We get the execution plan up again, and we'll find that it still uses an index, despite the fact that we're fetching over 20% of the rows from the table. There we go. So we can see still index range scan, output rows 1250, 39 buffer gets compared to 44 for a full table scan. See, so this is huge. You know, this is a really huge impact on how effective that index really is. It's gone from being useful for basically fetching 1 or 2 rows to over 20% of it. So this is a really big deal, the clustering factor. Oh, so if let's just shrink this down again, bring this back up. So just to kind of help visualize this, if you imagine these are across the top here are the blocks. For that primary key, so the M&M ID, the first few values we're interested in, so the ones between 1 and 550, are all in those first couple of blocks in the table. But when we went for it by weight, they're scattered all over the place. And more importantly, it's not just that they're scattered all over the place. That first one we read that was 0.7 a gram, that might have been over here. Then we might have had to go all the way over here to get the next one, and then back over here to get the next one. So we're continually skipping backwards and forwards between which block we're actually accessing. So as I said, this is huge, right? This is really big for how effective an index can be. So the next question most people ask when they learn of this is, how can I improve the clustering factor? How can I get it so that the data in the table more closely matches the order of the data in the index? So before we answer that, first thing to be aware of is that when you create a table in Oracle, by default, it's a heap table. This means that Oracle just inserts the rows wherever there's space in the blocks. So just like if you drop an extra grain on this pile of sand, you don't know where it's going to end up. It might land on the top, it might fall down to the bottom. When you insert a row in a default heap table in Oracle, you don't know exactly which block it's going to end up in. It could end up in any of them, or any of them that's got space. So does that mean there's nothing you can do? Well, no. There are some data structures Oracle provides to enable you to force the table structure. And one of those is an index organized table. What that means is, so normally when you've got a table, you've got two data structures. You've got your table here and your index here. Two separate data structures which can have different physical orderings. With an index organized table, what Oracle does is essentially combines those two data structures into one. So rather than having a table and an index, you've just got an index. So the table is now an index, and it is physically sorted in the same order as the logical ordering imposed by the index. So if it's by color, they'll be sorted alphabetically by color, blue, brown, green, orange, and so on. So some of you might be saying, well, why don't we just make all tables index organized tables? These sound great. They're really going to improve our clustering factor and make our indexes much more effective. Well, there are some restrictions around them, but one of the most important things to be aware of is that the index for your index organized table must be the primary key of the table. So if we wanted to create that index, make it index organized by color, we can't do that. Color's not unique. We would have to do something like, you could get clever and do something like create a fake primary key, add something to it, color, and then ID to make it unique. But that's getting a bit dodgy and cheating a little bit. So the data has to be, you can only do this on the primary key index. So does this mean they're completely useless? Well, not necessarily. There's a lot of tables where you might have compound keys. And these are typically things like master detail relationships or many-to-many join tables. So for example, you've orders with all those order items in them. You've got the order ID and the item ID. Everything for all those orders for the same, all the items for the same order have the same leading column order ID as the part of the primary key. So if you made that index organized, you know that all the items for a given order are located as close together as they can be within the table, because they're all sorted in the same location in the index. So if you have a compound primary key, like say master detail relationships, many-to-many join tables, this could work. So that's first thing to be aware of. But the other thing to be aware of is, of course, that if you sort the data in one order, so you sort it by color, there's a very high chance it's completely disordered by other attributes. So if we sort these M&Ms, if I line them all up by color, there's a good chance that they're completely randomly ordered by weight. And similarly, if I order them by weight, there's a good chance they're completely randomly ordered by color. So improving the clustering factor for one column or one set of columns generally, almost always, comes at the cost of other columns in the table. So that means if you're frequently querying the table on the other columns, so we've got two queries, we want to find how many there are of a given color, but I don't care what color they are. I'm trying to watch my figure. I want to keep my sugar intake down. I just want the lightest ones, the ones that weigh the least. They're going to be in different orders. So physically ordering them one way is going to mess up the order the other way. So you've got a trade-off. You've got to decide. Now, in some circumstances, one of those queries might dominate. You might run it all the time. You might need sub-second response. And other ones aren't so important. So for example, my daughter's going to come to me at least 10 times a day and ask me, can I have some red sweets? But if we have another attribute on expiry date, I only need to check which ones are expiring once a week or so. Chocolate doesn't go off that quickly. So it doesn't really matter if that query takes a bit longer, because we run it less frequently. I can schedule that overnight. I'm not waiting for the answer. So you've got to decide, make some trade-offs here. So you can improve the clustering factor by forcing it, but there are some things to be aware of. They say, yeah, you can use an index organized table. just another thing quickly. You have to do this when you define the table. You can't recreate the table on the fly to become index organized. So if you've got a standard heap table and think, I really wanted that to be an index organized table, or vice versa, you've got to recreate the table. You've got to create a new one and copy the data over. There isn't like an alter table index organized or something like that. And you might improve some queries, but at the cost of the others. But there's some other things to be aware of. So who has ever had a query that's run slow in production, they've copied the data, or they've tried to recreate and test and found it's chosen a different execution plan? They've not been able to, yeah. So now there's, again, this is something which there's many reasons for, but a common reason is that it has a different clustering factor. So if you've got your data ordered like this, like gray, orange, red, what you want is when you take it over to your test system, it to be in exactly the same order. However, if you've used something like data pump, export, import, just standard SQL scripts, download to CSV and then re-import, there's absolutely no guarantee it's going to end up in that same order when it goes into the test database. Because like I say, if you're using heap tables, that physical order could be completely reshuffled when it gets to your test database. And this may be enough to change that clustering factor so it's flipped from a full table scan to an index range scan or vice versa. So if you find you've got problems in production, can't recreate them in test, check that clustering factor. There's a whole bunch of other things that could go wrong. This also assumes you've got exactly identical hardware, yada, 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 which isn't always the case. But the clustering factor is a really big one. Now, there is a way you can get around this. This is one where you need DBA. How many people are DBAs here? Many? One or two? Most of the rest of you developers? Yeah. This is one you'll need help from your DBAs for. You can restore from a backup, which is a physical exact copy of the data as it was in production. So you need to go, can we have a physical copy of the database? And then the clustering factor, the physical storage of the data will be the same. But like I say, that's something you need DBA help for. And of course, if you've got super large databases which are terabytes in size, it's just not always practical to have a test database which is a complete copy of your production. So as I said, the colors could switch over. So, this is another thing you need to be aware of when you're developing applications as well. So let's say you're building a new application and business is really optimistic. You think you're going to be generating million plus rows a day, and you're pretty diligent. You build your tables, load them up with 400 million rows of test data because that's how the table's going to look in a year's time. And everything works. Everything runs nice and smoothly. But that random data you're generated may have no relation to the order it comes through in production. Let's say you pseudo-randomly generate people's names, but just happen to generate them in alphabetical order. So they're now all nicely clustered in your test database on that table. However, of course, in production, people are going to turn up in any random order. You're going to have Jim, then Dave, then Zoe, then Barry. You can't go to your customers and say, we want really perfectly clustered data, so our application is super, super quick. What we're going to do is give all of you a number, starting with Aaron Aronson and finishing with Zinedine Zidane. You've got a 2-minute slice of the year to do everything, place all your orders with our application, so that our data is perfectly clustered and it's as fast as it can be. You just can't do that. A lot of the data you get is just randomly ordered, and there's nothing you can do about that, short of forcing the physical data structure. However, there are some columns, which are going to be likely pretty well clustered. Anything which is an always increasing or always decreasing value, so common ones, sequence assigned primary key, insert dates, these values always go up. Now, it's unlikely they'll be perfectly clustered for various reasons, but there's a high chance that they're very well clustered. So this is where you need to use a bit of knowledge, intuition, guesswork about how your application might actually be used. And ultimately, to a certain extent, you've just got to do it and react to things as they happen in production. So do be aware, you might think you're making perfect test data, perfect test cases. Real world data is messy, and it's unlikely you'll be able to generate something in advance which fully mimics or really closely mimics what happens a year on in production. So as I said, the amount of work a full table scan does is constant in terms of the number of blocks it fetches. It always reads every single block, looks at every single row, sees whether it matches your where clause. An index, however, will only access the rows and the blocks that match the where clause. However, the amount of work it actually has to do for that comes down to how well the physical order of that data matches the logical order of the index. So quite often, when people start tuning SQL queries, they think about how many rows. Is it going to fetch one row, 100,000 rows? And you kind of do need to think about this. You know, if you're doing primary key lookups or other queries which you know are only going to fetch 1 or 2 rows, an index is going to be the best approach. But for other queries, which are going to fetch maybe 100, maybe 100,000, it's not so helpful to think about how many rows they're going to fetch. What you really want to think about is how many blocks from the table they're going to access, and how many times will they have to re-access the same ones, and how does that compare to the total number of blocks in the table. So if you've got table, if I have 100 bags here, if I get to a point where my index, I think, is going to have to pick up more than 100 bags, full table scan's going to be cheaper. So bear this in mind. And when you're tuning your SQL queries, look at that clustering factor, check what it is in production, check what it is in test. Are they the same? How are they different? And that's me. So have you got any questions? Yes? Go on.
So how much of this applies to other SQL databases like MySQL or Postgres? Is this Oracle specific or general?
So the question is, how does this apply to other SQL-based relational databases? And the answer is that basically all of them have the same principles. They have different names, like SQL Server calls them pages rather than blocks. But the principle is still the same. That physical ordering of your data still impacts how efficient your queries are. And if you think even things like Hadoop and other kind of NoSQL type approaches where they have sharding, it becomes even more important, because then are you sharding, you're actually going across different physical servers, which are completely different disks and so on. Are you just visiting one of those, or do you have to go across multiple of them? So it really applies to all of them. I'm not too familiar with other NoSQL to know, but all SQL databases, there's variations on the theme, but it is principally all the same. Any other questions? Column-based databases. Oh, okay, yeah, that is a different method. I don't know enough to kind of comment exactly, but they do work in a different way because they compress the values and so on. So that is one of the exceptions, yes. Any other questions? No? Yes? Well, if you have more questions, feel free to come up to me afterwards. There's some M&Ms here. If anyone's hungry, feel free to help yourself. And like I said, if you have anything you want to know about Oracle or have problems with Oracle, go to Ask Tom. Things we could do better, reach out to me. Go on. So after you do an update, to drop them and recreate them. In terms of improving the clustering factor, or and we said so. So what? And we yeah. Hmm? Yep. In, so it's to reduce the time for the updates and the deletes, you mean? So the question is, in terms of, is it worth dropping your indexes to improve performance of insert, update, deletes, for example, for ETL processes? Yeah. And the answer is, it does kind of depend. You know, if you are only deleting a handful of rows, dropping those indexes to have to recreate them all, that's, you know, a waste of effort. You have to, particularly, let's say you've got 100 million row table, you're just affecting a very small fraction of those, a few hundred, a few thousand. You're going to have to, you drop the index to save you updating the index for a few hundred values, then you have to rebuild the index for all 100 million of them. That's a waste of effort. However, if it's 100 million row table and you're updating every single row in the table, inserting, deleting, and modifying them, it might help. Ultimately, it's something you need to test for yourself and verify on your data and see how it works. Does that help at all? Or okay, go on. So the question is, does it make a difference if you've got a row spread across several blocks versus multiple rows within one block? Yes. Well, the first thing to be aware of, so by default in Oracle, the size of a block is 8K. And typically, rows are nowhere near that big. So quite often in Oracle, you'll fit tens, maybe even hundreds of rows in each block. So it's pretty rare you actually have a situation where you've got one row which spreads over multiple blocks. So first answer is it's kind of rare, but there are some exceptions and some things to be aware of. We can talk to you more. But if a row does spread over multiple blocks, then it still has to pick them all up. So if you've somehow got a massive M&M which has magically spread over 3 of these bags, I've still got to pick up all 3 of them, which obviously makes the index less efficient because I've got to go and visit all 3 rather than just the one original one. So yes, an index, a row that spans multiple blocks will be slower, but there are some caveats, but generally it's a relatively rare thing. But I can talk to you more later if you want. Well, yeah, exactly, yeah. Any other questions, or are we, I think we need... And in, and so you're saying if
not index by, but index organized table.
so if you update the values,
if you often update, it gets wasted very much space.
well, yeah, okay. So if you imagine an index which is on your primary key, which is a value which always increases. It's a sequence, and that's what your index organized table is. All new values, because it's always increasing, go at the end of the index. If you delete those old values over there, that space is dead. It's kind of gone because it has to physically sort the values into the correct location in the index. So if the top value is 1 million, my sequence is going to keep going up to 1 million. If I delete the values 900,000 downwards, you're going to have empty space potentially, and it can't reuse that. If it frees the block, gone.
Never.
Well, if it frees the block completely, if it becomes completely empty, it releases it. But as long as there's something left in the block, that value which has 800,000 in it, that block stays in that location in that index. My 1,000,001 has to go over here, so I keep building up the index this way. So you can end up with wasted space if you delete entries, small numbers of entries from a table, from an index. But that's only if it's an always increasing, value. If it's something like your weight or account ID, which is kind of randomly generated, chances are it's going to get refilled at some point. Does that make sense? Any other questions? Yes? No? Anyone? Okay. Thank you. And come down if you want some chocolate.